Assalamu alaikum. So I'm going to talk about. So this is a course which I'm starting for those who want to learn the group theory, and this would be the first few things about few things which we should learn before group theory. So let's talk about some like very fastly some things which we should know. So we have sets. We are not giving any axiomatic treatment of the set theory, but we will only talk about the intuitive definition of the set theory. So, particularly a set as with only finite number of elements. Sorry. So a set S with only finite number of elements is called a finite set, and then S is called infinite set. Otherwise, we denote the number of elements like this in the set, and we quite often denote a finite set by listing its elements within braces like this. Then these are the elements in the set. The technique is sometimes used for infinite sets, like for instance, what we say that set of positive integers n, or we may be denoted by this, and there is no upper bound. So the definition is for an element to be in the set is let S be a set, X is inside S, X is not a member of S, or like not inside S. So similarly, if this is the set, then 1 is inside S, then 4 is not inside S. And then A is a set A. A set A is said to be a subset of a set S if every element of A is an element of S. And then we can write A subset sign S, and then say that A is contained in A. And if A is contained in A, but not equals to A, S, A is contained in S with not equals to S, then we can write that it is only a proper subset. That means it's properly contained in S, or it's a proper subset of S. And that is that this can be written as improper subset, but like 1, 2 is a proper subset of 1, 2, 3. And let A and B be two sets. Every member of A is a member of B, and every member of B is a member of A. Then we can say that A and B are the same or equal. In this case, we can write A is B. It is immediate that A is B if and only if A is contained in B and B is contained in A. Then we have the following theorem. The result says that we have two sets A and B, then A is B, or A is equal to B if and only if A is contained in B and B is contained in A. And we can prove this by using some proof techniques. Now, there is a concept of null set. The null set or empty set is the set with no elements. we usually denote it by phi. And for any set A, phi is always contained in that set A. Now every element of phi is an element of A since phi has no elements. That's you can say that it's an inclusion casually. We also describe sets in the following manner. Consider a set as the notation is this says that x such that x is inside set S, comma, p of x. Or you can say x is inside S such that p of x. Means that A is the set of all elements x of S such that x satisfy the property P. And that property can be anything. For example, we have natural numbers which we so let's and say it is an integers, and if we just so this P is that x is greater than 0. X is that's the property. We know how to do union. So we have two sets. If we just combine the elements of x, all those x in A and all those x in B, then we will get the union. We know the intersection, that if we just take those elements which are common in A and B, that would be the intersection. Then we have this theorem which says that we have two sets A and B, and following are equal. So following holds. If A is contained in A union B and B is contained in A union B, and A intersection B is contained in A and A intersection B contains also in B. That was what we have discussed here. That is the meaning of union and intersection. The union and intersection of two sets, A and B, is described pictorially in the following diagrams. The shaded area represents the set in the question. So we are saying union can be denoted by this, and intersection can be denoted by this. Okay. Now, when we say that two sets are disjoint, when there is nothing in common between them. Let's do some examples. So let's say A is this set, B is this set, then this is their union, just as combine 1, 2, 3, 4, 5, 6. Intersection is 3 and 4 only. And if C is this set, then A union C is this one. While A intersection C is phi. So A and C are disjoint. Now, the important thing is, note that the union and intersection have been defined for two sets. These operations can be similarly defined for any finite number of sets, that is, and then union denoted by this sign, or you can also denote like this, and is the set of all elements x such that x is an element of some AI, where I is between 1 and n. The intersection of all these sets can also be denoted by this sign or like this, and is the set of all the elements x that are in every I, for all I. We say that I is an index set for a collection of set A. For any alpha in I, there exists set A alpha in this collection A. A is, then this is collection of sets. I can be any non-empty set, finite or infinite. The union of the sets A alpha, where alpha is an I, is defined to be the set this x such that x is an A alpha for at least one alpha in I, and is denoted by union alpha and I, A alpha. Similarly, the intersection of the sets A alpha, where alpha and I is defined to be the set x such that x in A alpha for all alpha in I, and is denoted by this signature. Then we talk about the complement, or we can say relative complement. So we have two sets A and B. The relative complement of B in A, denoted by the difference, is the set x such that x in A but not in B. And this is the following diagram for A difference B. So example, A is this set, B is this set. If we just minus all those similar elements from A, we will get A difference B. Now, this is the concept which is very, very important for all of the mathematics. And we define it. So we have a set A and a set B, non-empty. These are non-empty sets where and x is in A, y is in B. Then the order pair x comma y is defined to be the set x comma y, the Cartesian cross product, Cartesian product, you can say A and B is written as this and defined to be the set of all the order pairs for the elements x and A, y and B. The property that when two order pairs are same, so let's say this is an order pair and this is an order pair inside the Cartesian product, then we have we claim that we claim that if and only if x is z and y is w, then these two order pairs are same. So first suppose that x is z and y is w. Then we have this set is equals to this set. So these order two pairs are same. Now suppose that x comma y is equals to this, then we have these two sets are similar. Now, since this x lies inside the set, it follows that this x lies also inside the set. This implies that either x should be z or x should be z comma w. But if x is z, then we must have x comma w is z comma w. From this, it follows that either x is z and y is w. Now, if x is z comma w, then we must have x comma w, x comma y is z. This implies that xw is z, xz is w, and xy is z. Thus, in this case, all of them are equal. This established our claim. It now follows that if A has m elements and B has n elements, then the order pair has m cross n elements. So we can see that if A is this set, B is this set, then A cross B would be equals to all these order pairs like this. For the set R real numbers, the Cartesian product is merely the Euclidean space. All of the points on 2 by 2 plane, x comma y plane, you can say. For any set x, the power set of x written by this is defined to be the set which contains all of the subsets of x. So let's say we have x as a set, then the power set of x is this one, which contains 5, 1, 2, 3, 1, 2, 1, 3, 2, 4, 2, 3, 1, 2, 3. And then we can, so if x has 3 elements, so here you can say order of x is 3. Then the number of elements inside the power set is 2 power 3. So if order of x is n, then order of p of x is 2 power n. This is the thing we should know. Remark. So let P and Q be some statements. Throughout the test, we will encounter questions in which we will be asked to show that P, if and only if Q. That is, show that the statement P is true if and only if statement Q is true. In situations like this, we first assume that statement P is true. That P is true, and show that statement Q is true. Then we assume that Q is true, show that statement P is true. The statement P, if and only if Q, is also equivalent to the statement if P, then Q, if Q, then P. For example, see the workout example. Now, proof for sets A and B that A is subset of B if and only if A union B is B. Now, this is P statement, this is Q statement, right? Now, first we will assume that A is contained in B. We now show that A union B is B. So let X be the element of A union B, then this shows that if it is inside the union of A and B, then this shows that it either lies in A or it lies in B. And this implies that either X is an element of B, implies that X is an element of B since A is contained in B, because we have already assumed that. We have this information, we have deduced this information that if X is an element of A union B, then it either that X is lie in A or it lies in B. And this implies that X lies in B since A is contained in B. So we just find that every element of A union B is an element of B. And we have contain. So A union B is contained in B. Now what we need to do is we have to show that every element of B is also contained in A union B. And which can be shown by theorem 1.1.41, in which we have said that if A union B is for a union A union B, B is always contained in the union, A is always contained in the union. So for this, we will just use B is always contained in the union of A union B. Hence, we have proved A union B is B. Now, converse, we will suppose that we have the union, which is equals to B. Then by the similar theorem, we can say that A is contained in the union. Since A union B is B, it now follows that A is contained in B. Because if A is contained in the union, then A will contain in A and A will contain in B. So this shows that A is contained in B. Okay. Then we have another example. Which says that, let's check the time. We'll do one more. Let's do the number 2. So we have the state. We have a state for a subset A of a set S. A complement denote this. A complement is called the complement of A and S, and we have let A and B be subsets of S. Prove that prove the De Morgan's law. Prove that what we need to do, first we show that A intersection B whole complement is contained in A complement union B complement. Then we will show that A complement in union B complement is contained in A intersection B whole complement. The result follows by the theorem 1.1.1. Okay. Let's take an element from A intersection B whole complement. We know that A intersection B whole complement can be denoted by this sign. Is this way, that all those elements inside S which are not inside the intersection. So this X is inside S and not inside the intersection. Also, X is not inside the intersection implies that it is neither in A, neither in B. That means X is inside S and X is not in A, then it surely is inside the A complement. Because if you exclude all those elements from S, then it will surely lie. And if X is inside S and X is not inside B, then it is inside the B complement. Thus, there are two options. Either X is inside A complement or inside the B complement. But why not? It lies inside the union. So that means that A intersection B whole complement will lie inside the union of, is contained inside the union of A complement union B complement. Okay. Then we have one side. Now we will prove the other side. We will show that the A complement union B complement is contained in A intersection B whole complement. So let's take an element from the union of A complement and B complement. Then this shows that either X lies inside A complement or it lies inside the B complement. And suppose it lies inside the A complement. That means X is inside the S, not inside the A. For sure. Since this intersection is contained in A by the theorem 1.1, part 2, then we know that it is not inside A. We also know that X is not inside A. Then we must have know that it is not inside the intersection, because the intersection is inside A. And if X is not in A, then it can't be inside the intersection. This implies that it should lie in all those elements in a set which does not contain the elements of this intersection. So we can show that if X is inside B complement, then it is not inside the intersection, then it is inside the complement of the intersection. Hence, we have this union contained in the complement of the intersection, and consequently, we have this De Morgan law. Exercise 3 shows the union and intersection of three sets. It's simple. We will do that. And this is the exercise. Problem 1 is very, very important. 2 is also important. 3 is also important. We have done one case of that. We can do by using the same arguments, we can do the similar one, and you can also prove the symmetric difference. So the symmetric difference can be found by union difference the intersection. Or the other way of finding the symmetric difference is finding A difference B union B difference A. And if you can write the proofs of these statements, write the proof if the statement is true, otherwise give a counter example. There we will end our first lecture, and then we will start talking about the integers in the next one.